Good morning, everybody. Like Dr. T said, we're a teammate. Myself, I'm Errick Santana. This is Orangel, Velasquez, and Andres Gomez, and we are the Heatstroke Cooling Shelter. For our problem statement, basically what our design initially was, as you can see here, is a collapsible shelter that we can hang, and it'll hopefully, in the principles, would be to prevent further damage of someone suffering heat stroke. So once you have somebody in that case, we're hoping that we can put this shelter around you. We can cool you down to a given temperature to at least wait for paramedics or anyone else to come and take care of you the rest of the way. For our objectives, because this was based for the ASHRAE competition, there were a lot of requirements that were set forth for us. One of the main examples, as you can see, is when you're suffering heat stroke, your body temperature goes over 100 degrees, and from that point you can suffer death if not treated. So the principles are, what we needed is to build something that could fit in a 3-foot by 3-foot storage, as well as be able to set up within 10 minutes. One of the other things is we needed to be able to hold a temperature for an hour at just a constant temperature held for an hour, as well as bringing a given temperature down within the 10-minute time span. The other objectives is that with this competition came different characteristics. So for example, one competition was held in California for its hot and dry climate, while the other was held in Georgia for a much dense air. So with the dense air would have other aspects that we had to take into consideration. The other thing we wanted to do is we used a small power supply to generate our fans, just because we wanted our area, because most of the time all we were supplied was a 12 volt source. So from that we had to know how to take care of the rest of the electrical equipment to get what we needed out of it.
Some of the engineering standards that we have to abide by in this competition, one of them is being the ASHRAE handbook. That one will tell us what our parameters, as Errick mentioned, that are 3x3 dimensions that we needed for our shelter, and it will give us what the climate was, what's the person that we have to treat it to. Another standard that we have to really take into consideration is the ASHRAE 55. That one tells us what is our shelter supposed to, the material that we're supposed to use due to the environmental impacts that we have on the outside and the inside. And also we're using the OSHA heat index guide. That one will tell us that depending on the humidity, depending on how the climate is outside, the temperature of the body can rise or lower depending on how the person, if is suffering from a heat stroke or is in a very hypothermia specific. Some introduction that we use in our project is about heat transfer. A little bit about it is that heat transfer is just an exchange of thermodynamic between physical system by dissipating heat. It could be either by temperature differences or by pressure. Some of the mechanisms that we know that about heat transfer are conduction, convection, radiation, and vaporization. Our project mainly focused mostly on is convection and vaporization, since conduction is not so much introduced into our projects, since the thermal skin of our body is about 0.02 meters, the distance between them, so conduction is not so needed. We have to take into account, but it's so minimal that we're not considering it too much. And radiation, since our shelter is going to be mostly in the shaded area, there is some radiation going on, but we're not taking too much into consideration about it. So for the convection basically is just fluid motion by air or by liquid that transports through a surface or through any object that we wanted. There's two types of convection that we have. There's free convection and forced convection. The forced convection is just fluid external force applied on the object that we wanted, such as, let's say you have a fan that is being applied on a microchip on the computer. Inside air is being blown, it dissipates heat in the microchip, and your computer doesn't get too fried or back on. And the other one that we needed to use is vaporization. Vaporization is basically once water is being evaporated in your body, the liquid behind it starts to cool down. That's when we start sweating. We cool down based on sweating or depending on exercise or hot climate. Our system, what we wanted to do is that to be able to calculate vaporization, we're going to use it as an open system. And using the first law of thermodynamics of an open system, we can use this equation to figure out how much heat is being emitted from our human body based on the enthalpy and the mass flow being evaporated from our body. So for our design, what we wanted to do is we want to create a shelter. We basically went with a cylinder about 3 feet diameter that will enable us to do a vortex motion with the person sitting inside. And we're going to use like a harness system to hang the shelter based on a high point such as a tree or any structure that is able to hold the shelter in place, and we're going to be able to use a pulling mechanism to pull down the person and create that vortex motion that we want.
All right, for the major components, we have 2 fans, an in and out fan. This one's dissipating air outside, this one's bringing air inside. And our main component of this project was the Peltier plates. A Peltier plate is a simple device, a little plate, that when you apply voltage to it, one side gets really hot and the other one really cold. So we're using this fan to dissipate the hot outside, and the other side of the Peltier plate, the cool one, is going to be using this fan to put air inside our system. This is our power supply, which comes from a big computer if you're trying to do it. We're trying to minimize our cost, and I'll show you later. Our material, we're thinking of making it clearer, like white, but it wasn't fireproof. If it didn't have a fireproof material, and it would make our cost go a lot up because we're throwing electricity through it, we're throwing cables and everything to it, so we wanted to keep it fire retardant material. And for our main structure, to keep the cylinder thing, we started building and we tried to make a perfect circle with a material or something, and it was really hard, so we figured out that if you use hula hoops and you reinforce them inside, it holds the project perfectly, and it holds perfectly. We'll show you later. Next slide. For cost analysis, we didn't want to spend more than $200 because we assumed that's what someone will buy a system like this it will cost, because we are beginning, when we started calculating the thing, we were going up the $800s to $600, which is not viable for someone to buy a shelter that's supposed to be portable and everything. So what we did was we cut in our expenses in half, pretty much, to $200, and the only way we could do it was using a cheaper material and smaller fans and less fans. But we wanted to, this is experimental, so we wanted to actually build something and see if we get some results. This is just a typical day of building our prototype. We started by sawing the material. He's really good at sawing. Next. Here you can see we finished the thing and we put the actual structure inside. This is all components that are going to be together. As you can see here, you have the fan throwing the hot air out. You have the Peltier plate there, and then the cool side is throwing it inside the system. As here you can see our main structure already built in. We had to use these little panels for safety reasons, so nobody sticks their finger in and when they're being cooled inside, and because it's rotating. And this is one of the final products. Here you can see we started wiring the whole thing. We used 2 plies, so we could throw all the wiring in the middle, so you don't have any wiring, and it looks decent. You can see we strapped it here, and it was a little bit shaky, so we added another structure thing, so it holds the cylinder shape.
So for our testing that we use, we have, as Eric mentioned, that we have 2 other conditions that we have to take into consideration: the humid hot climate and the dry hot climate. So for our test subjects, we were able to use simple objects as like a silicone glove and a bunny plush toy. I'll explain why later. And to measure the temperature differences, we're able to use an infrared electronic thermometer to be able to pinpoint the exact temperature at that exact point that we need. So for testing, for the silicone glove, the thing is that with the silicone glove has almost the same thermal conductivity as the skin. So that's what we use that as one of our controls subjects. And for us to be able to know if a temperature difference is being dropped or not, we use a control, meaning that we measure the temperature outside and then we have a temperature inside. So we were measuring back and forth in an intervals of like about a minute, 2 minutes, and 3 minutes, so on, all the way to an hour to see and compare the results between the inside and the outside of the testing. And when the inside, with the heat transfer, we're using convection, so the fan, like I explained before, there's forced convection, so there's air flowing inside, and that would allow us to cool down the glove inside. Then for the plus toy, well, basically what we did is that we drenched the plus toy on water, we put it in the microwave, and then we took it out quickly. What that allows us to do is evaporation. That's something that we need to take into account for how fast or how quick is evaporating from a system that we needed. And we measured both in the two arms, in the head and in the torso, and we wanted to figure out what the temperatures are going to be in the inside and in the outside too. So we have a control and experimental. As you can see, the bunny is really active. So here's results that we have for the humid hot climate. Basically in Florida it's like not so perfect weather. We have humid hot, and then some days we have dry hots. So we have to, some days in the summer we were like going out, we were trying to check the day to see which days are better to test our subject. And for the humid hot climate, we saw that in the controls, you see in the dark blue line that it's still decreasing, but our experimental is decreasing a little bit faster, meaning that our shelter was working in somewhat good, but it took like about almost like an hour to just drop down like about 20 degrees. And we did the same thing for a dry hot climate. In a dry hot climate, the thing is that now there is no humidity. Humidity traps heat. And in a dry hot climate, you're supposed to have more heat transfer by convection, and there's no trapping of water in the atmosphere. So what we did for the plus toy, we did both graphs. We measured both the head, the left arm, the right arm, and the torso. And we have our experimental and our control. As you see in the trends of the control, the temperature drops. But when we do it on the experimental and inside of the shelter, our temperature drops is very significant, very high. That will tell us that our shelter is working in a fast rate and efficiently than what we wanted. We did it for both hot and dry climates. Same thing that we did is we did a control and experimental, and our theories proved to be right when we did it with the plus toy. So our results, based on the mechanisms that we use for multiple mechanisms, the efficiency is not what we wanted. According to the manuals and everything, their efficiency is supposed to be like about at 10%, but when we calculated the efficiency, it was relatively like about 1-2%. So we're thinking about what we can do is maybe add more fans to the system, and that way we can do more cooling, and that will help us efficiently drop the temperature of the person faster than what we instructed to be done.
For the social and global impact, if this ever becomes a successful mechanism used for cooling, we wanted to make it a public thing, so available to everyone to use. We didn't want to make it private and just profit out of it, because this is supposed to help people out. So if it ever becomes a successful thing, we want to make it all public and everything so people could still work. And this is an ASHRAE competition, so all this data could be used for anyone else to implement new stuff or use our existing idea and make it better. We also wanted to make everything recyclable. All the materials to be recyclable. That way, if you ever want to get rid of it, you can just recycle all the materials. Lifelong learning. We really learned a lot about time management, because time flies when you're having fun. We also learn about the economic side of the engineering, because usually you're just doing math, you're just learning stuff, and you don't take into account how much someone spends when making an actual product or a prototype. We started with thinking we were going to spend $100, $200. It went up to 800 when you start doing the economic side. So it teaches us the economics of balancing out so we could make a viable product.
Okay, as for our member responsibilities, as you can kind of see in some of the other photos from previous, Andres was our team leader, and he did a lot of the initial research on how we were going to have this come about. You also had myself, I was design and manufacturing, so this is mine. And then you have Orangel, who did a lot of calculations and testing. This is our actual timeline that we feel we did a pretty decent job coming to the end for testing and everything. We made the deadlines we had anticipated on making. Okay. In conclusion, like they had both said previously, this isn't perfect. It's not exactly how we wanted it, but we can proudly say that we were able to take into account all the given parameters and still have at least some kind of success, both in dropping the temperature and holding the temperature for the given times. We know that at a later point, like I said, you know, this was sponsored by the three of us, so our funding wasn't very high, so we had to do the best we could with what we had, and that we can confidently say we did do. And for future work, the same principles. If for the next group that decides to compete in the competition, they hopefully can get some extra sponsorship. Like we said, we initially planned on having 6 fans compared to the 3 that you see here. And we've done the calculations, as Orangel had said. You know, if we have more fans, if we have a better structure set up, we'll be able to get more cool air coming through, as well as all the requirements are made, cooling it faster, cooling it longer, and the rest of that. Special thanks to the people that had helped us, both of our advisors, Mr. Tremonte and El Sahab, as well as some of our friends who helped us with building, even though we didn't picture them in some of those things, but you know, thank you guys. And that's it, thank you.
Questions?
You know, I brought this up while you guys were presenting this last time, but you did more research on this than I have, so you might know the answer better than I do. But the human body, just sitting down, is probably like 100 watts an hour. Where if you're really working out, it might be doing a kilowatt or 1.5 kilowatts an hour. So I know you could calculate how much heat you could remove from there. So would you, if somebody's really overheating and producing a kilowatt of heat, would you be able to remove that amount as well? So you not need to, in my opinion, you would have to remove what's being generated by the body on top of what you want to cool off. So a glove with just hot water will show you that you're removing heat, but I don't know if it's efficient enough to remove the heat being generated by the body.
Due to money, if we were able to put 6, 8 fans, we're able to take out a kilowatt of air efficiently. Things that we don't have money. We have $200 to work with. We want
So
to
how
make
much
it
are you
cheap.
removing now?
Right now, well, generally a human being, as you mentioned, that it removes generally like normal metabolism, like about 100 watts. What we have to remove, well, we really generate like about 800 watts, pretty much. Our main calculation was that for a person averaging out like 150 pounds, they have to be able and dropping the temperature by like 5 degrees, taking into account calories and kilocalories and burning. We have to be able to remove like about 2,400 watts. So our system only, like with just 3 fans, generates only 800. So if we put more fans, probably we're gonna remove more. That's what we needed to do.
Okay. The questions I want to ask, the first one I want to ask about is the assumption that you've got a tree or something close by.
Yeah,
to be
we
able
have
to
the
hang
slides
it-
for future
hang
work.
this
We
on.
want to make an own standing thing. But
Well, my question is, why didn't you design it so it straps to the shoulders? So that, you know, you basically put the person in this thing, so now all of a sudden it's going to freestand on its feet.
if you strap it on someone that's not even conscious, you can't strap something on someone that's conscious. So it's like the easiest one is someone you should put it down in a little chair or something, and then you put the thing on top of them.
Or it spring loads up.
Yeah, or springs loads up from up and down. Because if he's knocked out, you can't move him, put him. If it's a heavier person, the closest thing you can do is just put him in a little seat and put the structure around him.
Okay, and then the second question I have is, the whole top is open, and you've now got 2 fans, one pumping in and one pumping out. How much value are you losing due to the fact that you've got an open top end to the system? Wouldn't it be as effective or more effective to use both fans to pump in with an exhaust coming out of the top?
The outside fan is not used for cooling or anything. It's just simply to cool the plate. Because if you cool the hot plate faster, it gets cold faster. So it's a give and take situation. It's a 50-50 thing. If you're not cooling the hot part of the plate enough, it's not giving enough cooling.
But you had 2 fans.
Yeah, the inside fan is throwing the cold air.
Yeah.
The fan outside, as you can see here, the fan outside, this fan, is just throwing the hot air from the plate out.
It's like a
So
condenser type thing.
Plate sandwich between the two.
Yeah, it's like a sandwich between the thing, yeah.
Well,
And that's why we have bigger, the one on the inside than the one on the outside. The one on the outside is
There were
smaller.
3 fans then?
There's 2 fans. But the one on the inside putting air is bigger.
Hold on, I think now I understand what it is you're asking, because we do have, you see here, you have the outside fan, and as Andres was telling you, the Peltier plate's hot side, the colder you make the hot side, the colder the cold side becomes. So like you said, this fan here is dissipating the hot side, and we have these larger fans here.
Right, now
That'll
those
be
are the
bringing
fans
the
I'm
cold air.
actually talking about.
Right, now the thing is, we actually have 3 fans set up here that are sending cold air in. So we don't actually have air out. The air out would technically be what is already on the outside of this.
It's sealed.
Okay, thank you.
Now, that brought up another point I forgot to mention, I had written it down. You're talking about an unconscious person, you really don't want to have them sitting up. That person should be laying flat.
Okay, the thing is that we want to lay him flat. We have like our parameters in our project. We lay him down, there's less surface area that we gotta.
I understand that, but he's gonna die faster if you sit him up.
Yeah, this is all experimental, so nobody's gonna die. It's just to test something, so. Yeah, if you wanna build this for real, you gotta invest millions of dollars.
No,
in
but
it,
what
yeah.
I'm saying is it's very important if somebody's unconscious to have them flat. So
Yeah.
just keep that, you could probably make a cone or something on it, but just, I understand for heat purposes, it's better to be vertical.
Yeah,
But for health reasons, you want to lay horizontal.
A quick comment towards your Peltier efficiency, especially in a humid environment. Getting the cold side colder isn't necessarily the best thing to do because of condensation. And what you'll often find actually is you will eventually ice over your Peltiers.
humidity, yeah.
With high humidity.
Yeah.
Because, for example, in South Florida here, the dew point 72 degrees roughly at an 80
Yeah,
Fahrenheit.
crazy Fahrenheit,
Yeah,
too much, yeah.
80%. So as soon as that temperature gets below 72 on the surface of that plate, you've got condensation
Yeah,
forming.
condensation.
So that's going to kill your efficiency.
I noticed you tested a bunny and a sleeve. Why didn't you test one of you guys?
Because I was smarter than you.
I
I had no guarantee.
fellow that designed it and built it, you know,